Today, we're diving into a material that might just be one of the biggest chemical breakthroughs of our time. People have called it the ultimate sponge, a solid material that can soak up just insane amounts of gas. And it's built, quite literally, one atom at a time. So just imagine for a second, what if you could build a material from the ground up? I mean, picking out your molecular building blocks, just like Legos, to create this perfect porous structure. And what if that structure was so incredibly full of holes that it was actually like 90% pure empty space? Sounds a little bit like science fiction, right? Well, it is very, very real. So how in the world is that even possible? All right, in this first part, we're going to pull back the curtain on the incredible technique that lets chemists design and build these materials with, pinpoint atomic precision. Okay, so the official name for these things is metal organic frameworks, or what everybody calls them MOFs. And they are a totally revolutionary new class of materials. They're crystalline, they're porous, and they're made by linking these metal-containing units together with organic molecules. And the result? You get this huge, wide-open framework that's really just changing the game in chemistry. Now, the secret sauce behind MOFs is this concept called reticular synthesis. This is not your typical chemistry where you just mix some stuff together and kind of hope for the best. No, this is all about design. Chemists can pick specific molecular building blocks and link them together into a structure they've already planned out. So they aren't just discovering a material, they are straight up designing it. And the recipe is actually pretty simple to wrap your head around. First, you start with these metal-containing units. Think of them as the hubs. Then, you add in organic linkers that act like molecular struts to connect everything. And when you mix them, they just self-assemble into this strong, perfectly ordered, and unbelievably porous crystal. That Lego analogy? Yeah, it really, really works. Now, because you can swap out those metal and organic Lego bricks for different ones, the possibilities are, well, they're practically infinite. Just get this, in the last decade alone, scientists have created and studied over 20,000 different types of MOFs. Let that sink in. This isn't some tiny little niche in science, it's a straight-up explosion of discovery. So you might be wondering, why does all this perfectly ordered empty space matter so much? Well, that brings us to the true superpower of MOFs, a property that is honestly kind of hard to believe when you first hear it. It all boils down to one simple thing: surface area. See, because these frameworks have pores on a molecular level, their internal surface area is just massive. All of those tiny internal walls and nooks and crannies, they all add up, creating a material that on the inside is way, way bigger than it looks on the outside. Just how massive are we talking? Okay, let's just look at the raw number for the current champion. It's a MOF called NU1110. Its surface area has been measured at 7,140 square meters per gram. A single gram of this stuff. Wow. Okay, to put that number into perspective, imagine you have 1 gram of this powder. That's about the weight of a paperclip, right? Or the size of a sugar cube. If you could unfold all of its internal surface area, it would be enough to cover an entire American football field, end zones and all. That is the kind of power we're talking about here. And just to see how big of a deal this is, let's compare MOFs to the stuff we've used for decades, like zeolites and activated carbons. I mean, look at the pore volume, basically how much empty space they have. Zeolites and carbons, they're pretty good. But then look at the MOF, NU110. It's not even in the same league. It's not a small improvement, it's a huge leap forward, with over 7 times the empty space of activated carbon. So, okay, we've established we have this incredible sponge. The big question now is, what do we actually do with it? And this is where the science gets really exciting, because all that empty space and all that surface area can be put to work solving some of the world's biggest problems. Seriously, the list of potential uses is just staggering. That huge surface area is perfect for storing gas molecules. Think hydrogen or methane for clean energy cars. They can act like tiny, perfect traps for carbon dioxide, literally pulling it right out of the air. The pores can also be used as little nanoreactors for chemical reactions, or even for things like targeted drug delivery in your body and medical imaging. And let's get specific. There's a MOF called NU100 that holds the record for hydrogen storage. Another one, MOF 200, is phenomenal at soaking up carbon dioxide. To give you an idea, a gas tank filled with this stuff could hold 9 times more CO2 than an empty tank at the same pressure. The takeaway here is pretty clear. These are top-tier, record-shattering materials. And listen, this isn't just happening in some university lab.
The potential here is so massive that major companies, we're talking BASF, Mercedes-Benz, they've already started working on MOF-based fuel tanks for cars powered by natural gas and hydrogen. This tech is really moving from the lab into the real world.
And that brings us to the final and maybe most exciting part. What comes next? I mean, if we can already build these incredible molecular sponges, where does this technology even go from here? Well, the vision is to create a whole new generation of truly smart materials. This quote from the original researchers really points the way. They imagine materials with different compartments, where each little section is designed to do a separate job, but they all work together. So, picture a single material that can grab a molecule, move it somewhere else, and then transform it into something totally new, all inside one crystal. And you know what? They're already doing it. The next big thing is what's called multivariate MOFs. Instead of using just one type of organic linker, one type of Lego brick, scientists are now mixing and matching up to 8 different kinds into a single perfect crystal. This creates an internal landscape that's way more complex and way more functional. Which really just leaves us with this final, amazing question. Now that we have the power to design and build functional materials, literally from the atoms up, what challenges that we once thought were impossible are suddenly within our reach? From clean energy to clean water to better medicine, the possibilities really are just as vast as the empty space inside a metal organic framework itself.